All right, hi everyone. So it's just 1 minute past our start time, so let's get started. First of all, thank you everyone for joining. Welcome to week 5 of week 6 of the Introduction to NLP series with Women Who Code Data Science. Thank you so much for joining. Hope you were able to review the slides of the previous weeks and tried out some code from the notebooks. If not, no worries, you can access the recordings anytime from the Women Who Code website. And if you are new joinee to the series, don't worry, we will recap some of the learning from the previous weeks, and you can refer to them later as well. And so before we get started, just a few shout outs. So shout out to our amazing team of volunteers for putting together this series. We would not have had this series without them. All of them are panelists on this webinar. For this session, I, Rishika Singh, will be the speaker, and all of the other leaders will be present on chat to support you. And please feel free to reach out to us with any questions that you may have. Another shout out is to our sponsor, Home Depot, for putting together these much needed events for our community. Please do show your appreciation for them by retweeting the post, and this will be shared in the chat shortly. And again, please don't forget to follow us on LinkedIn and join our Slack channel. The links to these will be shared in the chat. For the slides, you can download them at this link, and it was just shared in the chat right now. And if you have any questions, please post them in the Q&A box, and one of the panelists will make sure to get that answered. And if you have any issues, please chat directly with the panelists if you are facing these anytime during today's session. So with that, let's get started. And today for week 5, we'll be going over text classification, specifically text mining and text classification. So for today's agenda, we'll be doing a recap of week 4. We'll do a brief introduction to machine learning and give a high-level overview of the various types of machine learning. We'll go specifically into supervised learning and then talk about text mining and its popular applications. Then we'll go into text classification. And then we'll switch gears, and in the second half, we'll do some implementation with Google Colab. And so for the first part of the session, I will be speaking, and then Jayeeta will take over for the implementation. And then we'll go over any questions and then just do a wrap up and next steps. And the final session for this series is next week. And as usual, we'll take a 10-minute break in between the theory part and the implementation part, just for everyone to get up and stretch and grab a glass of water or some coffee. So let's do a recap of week 4. So what we went over was word2vec, Stanford Glove, similarity scoring, the question answering process, and then an overview of BERT and where NLP is today. So word vectorization and word embeddings. Vectorization is a process of converting text into numerical representation. Embeddings are the types of knowledge representation where each textual variable is represented with a vector. And a vector space model is a statistical model for representing text information. There's various applications with text regression, which is a prediction of the next words. And this can be broken down into classification or clustering, such as document similarity. So the key to performing any of these, for processing natural language text and for extracting useful information from the given word, a sentence is, we use machine learning techniques and which require the string or the text to be converted into a set of real numbers. And this is why we go through this text vectorization process. So we actually convert the text into this numerical representation. And next we went into word2vec, and the fundamental idea about word2vec is it's all about context. This was introduced by Google in 2013. Basically you have this large corpus and you make a data set of these tuples, and each tuple contains some word X or a word in the context of X. And then you would use any sort of machine learning architecture to then learn to predict the context word of X given this word X. And the general assumption is that words that occur in similar contexts tend to have similar meanings. And we can actually break the similarity down into 2 types. We have semantic relatedness and semantic similarity. And so what we end up is this feed-forward shallow neural network model with a single hidden layer where each word is a vector. Word2Vec finds relations between words. And as I said, we kind of transform this unlabeled raw corpus into labeled data. And then we are able to learn representation of words in a classification task. Then we went over Stanford Glove. So with Word2Vec, it actually relies only on local info of the information of the language, and the semantics are learned for a given word is only affected by the surrounding words. But then with Glove, you can actually derive semantic relationships between the words from a co-occurrence matrix. And so this is all about global context. So Glove actually stands for global vectors. So it is an unsupervised learning algorithm for obtaining vector representations for words. And what we do is we find meaning in these statistics. So the relationship of words is examined by studying the ratio of their co-occurrence probabilities with various probe words denoted by K. And what we get is this resulting representation of linear substructures of the word vector space. And this falls under count-based embeddings, and this is where we need an upfront pass of the entire data during training. And next we have the different use cases that we discussed. I won't go too much into depth on these, but we went over similarity scoring, which is where we build, it's the building phrase or the document similarity model. And this includes BioSentVec and deep semantic similarity model. This also includes word mover distance, which actually helps to solve challenges of cosine distance. We also discussed combining various pre-processing and word embedding techniques. And here the main goal is to get the maximum number of questions to be answered with a high accuracy score. And we can also evaluate all of this with the confusion matrix. Next, we went over question answering, which is a research field composed of computer science, natural language processing, information retrieval, and information extraction. This is some applications were just a basic chat assistant and also information retrieval. And so lastly, we also talked about the state of NLP today, and this includes BERT. So here the base concept of BERT is word embeddings, where you have this feature vector representation of a word. And we also discussed the general idea of a transformer, and this is this novel architecture that aims to solve sequence-to-sequence tasks while handling long-range dependencies with ease. And the basic idea behind a transformer is to handle the dependencies between input and output with attention and recurrence completely. So BERT stands for bidirectional encoder representations from transformer. And it is this revolutionary NLP model that is, the state of the art when compared with traditional NLP models, and it's actually inspired many recent architectures as well, including Google's Transformer XL, OpenAI's GPT-2, Roberta, and several more are being developed. So with that, let's move on to today's content, and referring back to this NLP workflow image that we have been referring to for all these sessions, we're kind of going to this second to last stage of modeling and or pattern mining, and we'll actually also be doing a little bit of evaluation of our model. So just to get started on machine learning. So what is machine learning? It is a subset of artificial intelligence. It is a study of computer algorithms that improve their performance at a task through quote-unquote experience. And this experience is a formula that is built to generalize or fit most of your data. And so it is this general study of computer algorithms that allow computer programs to automatically improve through experience. And so an algorithm can be thought of as a set of rules or instructions that a computer programmer specifies, and a computer is able to process this. And so simply put, machine learning algorithms learn by experience, similar to how humans do. And so for example, after having seen multiple examples of an object, a machine learning algorithm can be able to recognize that object in new, previously unseen scenarios. And machine learning utilizes a variety of techniques to intelligently handle large and complex amounts of information to make decisions and or predictions. And to just clarify some terminology that's commonly used for machine learning. So we have our example data, or X, and this is a the data set containing information on certain qualities of objects or people. So for example, this can be a CSV file of pet information with the columns name, age, type, etc. So an example, and then, so with the example data, then we also have the target response. And this is a specific feature or column in the data set, which you would actually like to predict. So going back to that same example, this could maybe be the age column from that same CSV file. And then next, just to give some more information on the terminology. So we actually have various different data types for the example data and this target response. So what we have is categorical, which is also qualitative. And this, for example, this can be, gender or yes or no, and you can actually assign some number, but there's no actual mathematical meaning. So this is when values that have 2 or more categories or buckets, and there's no explicit ordering. So you can have it colors like green, blue, red, but you can't necessarily say that green is less than blue or blue is less than red. Then we have numerical values, and this is some sort of quantitative measurement. For example, the height of a person or a stock price. So they're numerical in nature, and there is this explicit ordering. So for example, if we have the weights like 0.5 grams, 10 grams, 2.5 kg, we can actually order it like 0.5 is less than 10, which is less than 2,500. And then to go a little bit further, we actually also have continuous or discrete. So continuous is actually this infinite number of possible values. For example, how much rainfall was on a given day. Or we can also have discrete data, and this is where it's integer based, and it's often counts of something, like how many times did I flip heads when I flipped a coin 50 times. And under categorical, we also have ordinal, and this is a mix of numerical and categorical in a way. So it actually has some mathematical meaning. For example, if you have a movie rating on a scale of 1 to 5, you can actually say that a movie that has a rated 5 is actually better than a movie that's been rated 1. So the rating must be either 1, 2, 3, 4, or 5. So given that, we're actually going to go a little bit into the different types of machine learning. And so based on the availability and the data types of the example data that we have, machine learning can be broadly classified into several categories. And so there's 4 general categories, and these include like learning problems, we have hybrid learning problems, statistical inference, and lastly, learning techniques. And so these encompass several subcategories, but today we're going to be discussing supervised learning and unsupervised learning, which come under learning problems. Then we have semi-supervised learning, which comes under hybrid learning problems, and then reinforcement learning, which also comes under learning problems. So let's get into it. So supervised learning, so this is when the majority of practical machine learning actually uses supervised learning. And the algorithm learns from example data and associated target responses in order to later predict the correct response when posed with new examples. So it's where you have input variables or X, and then an output variable, say Y. And you use this algorithm to learn the mapping function from the input to the output. So you can kind of have this Y equals F of X. And so the goal is to approximate the mapping function so well that when you have new input data, so new X values, you can actually predict the output variables Y for that new data that you have. And so it's called supervised learning because the process of an algorithm learning from the training data set can be thought of as like a teacher that's supervising the learning process. So we know the correct answers, and the algorithm iteratively makes predictions on the training data and is then corrected by the teacher. And the learning stops when the algorithm achieves an acceptable level of performance. So, the teacher provides good examples for the student to memorize, and then the student then derives general rules from these specific examples. And supervised learning problems can actually be further grouped into regression and classification problems, which I'll be discussing a little bit later. But just for a high-level description, classification is when the output variable is a category, such as red or blue or disease and no disease. Regression is when the output variable is a real value, such as dollars or weight. And some common types of problems built on top of classification and regression include recommendation systems, time series prediction. So recommendation systems typically correlate with classification, and then time series prediction correlates with regression. And then we have some popular examples of supervised machine learning algorithms, and these are, we have linear regression for regression problems, we have random forest for both classification and regression, and we also have support vector machines for classification problems. And so from there, we can contrast supervised learning with unsupervised learning. So here, the algorithm learns from example data without any associated response. So this actually leaves the algorithm to determine the data patterns on its own. So this is where you only have the input data X and no corresponding output variables Y. And so the main goal is to model the underlying structure or distribution in the data in order to learn more about this data. And so this is similar to methods that humans use to figure out that certain objects or events are from the same class by observing the degree of similarity between said objects. And so another reason why it's called unsupervised is because there's no correct answers and there is no teacher. Algorithms are left to their own devices to discover and present the interesting structure in the data. And so a very common example is when you recommend movies to friends. And just like supervised learning can be grouped into different kinds of problems, we have the same case for unsupervised learning. And so it can be divided into clustering and association problems. So clustering is where you want to discover the inherent groupings in the data, such as grouping customers by purchasing behavior. And you can actually see this in an example of what a clustering problem would look like. Then we also have an association problem, and this is an association rule learning problem is where you want to discover rules that describe large portions of your data, such as people that buy X also tend to buy Y. And then we have some popular examples of unsupervised learning algorithms, and these includes k-means for clustering problems, and then we have the a priori algorithm for association rule learning problems. And from there, we come to semi-supervised learning. And so problems where you have a large amount of input data X and only some of the data is labeled, some of the output data Y is labeled, this is where we have semi-supervised learning. So we actually are trying to learn from partially labeled data sets. And so supervised learning requires the data set to be labeled either, and this is a very costly process, especially when dealing with large volumes of data. So these problems kind of sit right in between supervised and unsupervised learning. And it has this disadvantage of a very limited application spectrum. But to give an example, say we have a photo archive where only some of the images are labeled as either dog or cat or person, and the majority are unlabeled. And so many real world machine learning problems actually fall into this area. And this is because it can be expensive or time consuming to actually go through and label all of the data. And it might also require access to domain experts. Whereas unlabeled data is very cheap and it's easy to collect and store. But you can use unsupervised learning techniques to try to discover and learn the structure and the input variables. And then you can use supervised learning techniques to make best guess predictions for this unlabeled data. Then you feed that data back into the supervised learning algorithm as the training data. And then you use the same model to make predictions on the new unseen data. So you can kind of use the strengths of both unsupervised and supervised learning to sort of battle the disadvantages of semi-supervised learning, which is very common for any real world applications of machine learning. And the last type we'll be going into is reinforcement learning. So this is when an algorithm learns from example data along with positive or negative feedback to each prediction that the algorithm proposes. So the algorithm must make decisions, and these decisions bear quote unquote consequences. And so the human world, you can kind of think of it like learning by trial and error. So reinforcement learning is a training of machine learning models to make a sequence of decisions. So this agent learns to achieve a goal in some uncertain, potentially complex environment. And sometimes if you were to think of an example of again, artificial intelligence kind of faces this game-like situation where the computer employs trial and error to come up with a solution to the problem. And to get the machine to do what the programmer wants, the artificial intelligence gets either rewards or penalties for the actions it performs. And so the main goal here is to maximize the total reward. And so reinforcement learning employs the system of rewards and penalties to compel the computer to solve a problem by itself. And so in this case, human involvement is pretty limited to just changing the environment and tweaking the system of rewards and penalties. And as the computer maximizes the reward, it is prone to seeking unexpected ways of doing it. Human involvement is focused on preventing it from exploiting the system and motivating the machine to perform the task in the way that it is expected. Reinforcement learning is useful when there is no proper way to perform a task, yet there are rules that the model has to follow to perform its duties correctly. And a very common application that we can see nowadays is autonomous vehicles. So I'll just take a quick breather. We just went over kind of this high-level introduction to machine learning and the various types of machine learning. And for today, we're going to be focusing on supervised learning. And this is the complete end-to-end model that we'll be building from scratch in the second half of today's session. So in this breakdown of machine learning, we talked about supervised versus unsupervised. And today we'll be focusing on supervised learning. So just to get back into supervised learning, this is, again, when the algorithm learns from example data and these associated target responses in order to later predict the correct response when posed with new examples. And again, this is based on the data. So based on the data type of the target responses, you kind of split supervised learning into two categories. We have classification for categorical data, and we have regression for continuous data. So again, classification is a supervised learning task where the output is having these defined labels, where it's a very discrete value. For example, if you kind of just look at whether if an item has been purchased or not, you can assign a 0 or a 1 value to it. So that's a binary classification. You can also have multi-class classification, where there's more than two sort of categories that is data can be classified into. Then we have regression. So this is when the output is actually having a continuous value. And there's several applications here, but basically the goal here is to predict a value as much closer to the actual output value as the model can. And the evaluation is typically done by calculating some sort of error value. And so there's many applications of supervised learning. So we have situations where there is no human expert. For example, if we have, throughout these 4 examples, X will be the input data and f of X will be this value that we're trying to predict. So X is the bonding strength for a new molecule. So then we have f of X, which is the binding strength to an AIDS molecule. Then we have situations where the humans can perform the task but cannot describe how they do it. For example, if we have X as the image of a handwriting character, f of X is the corresponding ASCII character. Our third example is situations where the desired function is changing frequently. For example, if you have X, which is stock prices in the last 10 days, f of X could be recommended stock transactions. Lastly, we have situations where each user needs a customized function F. So X is this incoming email message, and f of X is the importance for presenting it to the user. So now to go a little bit deeper into classification and regression, which are these 2 subcategories of supervised learning. So classification is a technique for determining which class does it belong to based on 1 or more independent variables. And it is used for predicting discrete responses. So these target responses are categorical in nature. So classification is used to predict a discrete class or this label Y, and it basically involves assigning new input variables X to the class to which they most likely belong to based on a classification model which was built from the training data that was already labeled. So this label data is used to train a classifier so that the algorithm performs well on the data that does not have a label, or that it has not yet been labeled. And we basically repeat this process of training the classifier on the already labeled data, and this is how we get it to learn. And so some of the questions that you can think of that a classification model might help to answer are, is this a picture of a cat or a dog? Is this email spam or not? Will it rain or not? Is the borrower going to repay their loan? Is this social media post negative or positive? What is the genre of this particular song or movie? Or maybe what type of gene is this? And so classification is again divided into 3 other categories. So we have binary classification, where you basically have just 0 or 1 or just 2 categories. And then you have multi-class classification and you have multi-label classification. And there's various classification algorithms that are very popularly used. We have the K nearest neighbors, we have decision trees, we have random forest, support vector machines, and naive Bayes. We won't be going into depth into all these algorithms, but just so you guys are familiar with these algorithms and are aware that it falls under classification and supervised learning in particular. So for example, if we have a bag that contains 15 balls of the colors green, blue, and red, if we know that the diameters and the colors of 10 balls, then is it possible to predict the color of the other 5 balls based on their diameters? So in this example, the diameter is this example data X, and the color is the target response, Y. So moving from there, we have regression. And so a regression problem is when the output variable is a real or continuous value, and it's numerical in nature, such as salary or weight or height. And many different models can be used. The most simple of these is linear regression. And so it tries to fit data with the best hyperplane, which goes through the points. You can kind of see the example of this here. You have all this collection of different points in this 2-dimensional space, and you want to find this best hyperplane or this line that will best fit the data. So this is linear regression. And so it aims to model the relationship between a certain number of features and a continuous target variable. So if I were to give you 4 different examples, and you would have to select which one is a regression task. So if we had predicting age of a person, predicting nationality, predicting whether the stock price of a company will increase tomorrow, or predicting whether a document is related to the sighting of UFOs. Which one of these is a regression task? That is predicting the age of a person, because it is a real value, whereas predicting nationality is categorical. Whether the stock price will increase is a discrete yes or no answer. And predicting whether a document is related to a UFO is again discrete, a yes or no answer. And so this example that we have here, if you know the height and weight of 20 people and the corresponding age of 15 of them, can you predict the age for the remaining 5 people? So here we have height and weight as the example data, this input data that we have, and then age is the target response or the output. So from there, let's move into text mining. So text mining is the process of implementing statistical and machine learning models to draw insights and to accurately predict from the data. So far we have learned how to prep the data and to turn text into numeric values. And this week we'll actually be learning some of the techniques you can use to interpret and to draw meanings from this prepped text data. So this is very widely used in organizations that are knowledge driven. And this entire process of examining large collections of documents to discover new information or to help answer specific research questions is becoming increasingly popular. Text mining helps to identify facts, relationships, and assertions that would otherwise remain buried in the mass of textual big data. And so once extracted, this information is converted into a structured form that can be further analyzed or presented directly using all sorts of visualizations. If you have clustered HTML tables, mind maps, charts, any form of tables, etc. And so text mining employs a variety of methodologies to process the text, and this is one of the most important. Of these is using the strengths of NLP. And so the structured data can be created by the structured data created by text mining can be integrated into databases or data warehouses or business intelligence dashboards, and this can be used for descriptive or predictive analytics. So moving from there, we have text analytics, and this is the automated process of translating large volumes of unstructured text into quantitative data to uncover insights, trends, and patterns. So we combine this with data visualization tools, and this enables companies and organizations to understand the story behind the numbers and to make better decisions. So text mining, text analysis, and text analytics are often used interchangeably, and they all have the end goal of analyzing unstructured text to obtain insights. However, while text mining or text analysis provides insights of a qualitative nature, text analytics actually aggregates all of these results and turns them into something that can be quantified and visualized through charts and reports. And so text analysis and text analytics often work together to provide a complete understanding of all kinds of text. For example, emails, social media posts, surveys, customer support tickets, and more. For example, you can use text analysis tools to find out how people feel toward a certain brand on social media. And this is known as sentiment analysis. Or we can use text analysis tools to understand the main topics in product reviews, and this is topic detection. So contrasting with that, we have text analytics, and this is where we actually leverage the results of text analysis to identify patterns, such as a spike in negative feedback for a certain product. And this can provide you with actionable insights that you can actually use to make improvements on the product, or maybe fixing a bug that is frustrating any users of the particular product. And so we're going to go into a couple popular techniques in this space. So first we have concept extraction, and this is where we actually reconstruct a set of unstructured or semi-structured textual documents into a structured database. So this is a technique of mining that is the most technique of mining to get to the most important topic of a document. So if you were to look into the e-commerce context, concept extraction can be used to identify what a shopping related web page is actually talking about. This is very practically useful in applications like search relevance and product matching. Next, we have information retrieval, and this is where we automatically generate a summary or compressed version of the text with information that will be of the highest importance or relevance to the end user. So we actually obtain information system resources that are relevant to any sort of information, and we obtain that from a collection of resources. And so searches can be based on full text or other context-based indexing. And this is information retrieval is the science of searching for information in a document, or searching for documents themselves, and also searching for the metadata that is embedded into these documents. And this metadata can help to describe the data and help to create these data and this data can be also comprised of databases that contain text, images, or even sounds. So it's not constrained to only text data. Next, we have text classification, and this is the focus of today. So text classification is also known as text categorization or text tagging. And this is a task of assigning a set of predefined categories to free text. And text classifiers can be used to organize, structure, and categorize pretty much anything. For example, if you have new articles that need to be organized by topic, or if you have support tickets that need to be organized by urgency, or if you have chat conversations that need to be organized by language, or if you have brand mentions that can be organized by sentiment, and so on. And so a classifier can actually take this text as an input, then you analyze its content, and then automatically assign the relevant tags. And so text classification can be done in two different ways. We have manual and automatic. So in manual, a human annotator actually goes through and interprets the content of the text and categorizes it accordingly. This method can usually provide quality results, but it is very time consuming and expensive. The latter, automatic classification, actually applies machine learning, natural language processing, and other techniques to automatically classify the text in a faster and a much more cost-effective way. Next, we have document clustering, and this is where we bring together clusters of documents that have similar content. So we actually went over this a couple weeks ago, but just to give a brief description. So this is a method for finding structure within a collection of documents so that the similar documents can be grouped into categories. So the first step is to actually create word vectors for the documents that we wish to cluster. And this vector is simply a numerical representation of the document where each component of the vector refers to a word, and the value of that component indicates the presence or the importance of that word in the particular document. And then from there, the distance matrix between each of these vectors for every document that we have is then fed to algorithms, and this then helps us to group the similar vectors together into clusters. Lastly, we have text visualization, and this helps to simplify and enhance the discovery of useful information with visual cues. So here are some examples of those visualizations. And we have done some very simple visualizations when we were going over some pre-processing. It just helps to describe the data for you to extract some information about the data, and it helps you just view the data in a different way. And then from here, we're going to move into some popular applications. So first we have concept extraction. So information extraction, or IE, is a technique to automatically extract a piece of definite structured information from unstructured or semi-structured data in the form of text using natural language processing. So this task of automatically extracting this information can be done from machine readable documents or other electronically represented sources. And so in most of the cases, this activity concerns processing human language text by means of natural language processing. And some recent activities in multimedia document processing, like automatic annotation and content extraction, can be done out of images, audio, video documents, and this is all seen as information extraction. So a very broad goal of IE is to allow a computation to be done on the previously unstructured data. But a more specific goal is to allow logical reasoning to draw inferences based on the logical content of the input data. And so structured data is semantically well-defined data from a chosen target domain. And this is typically interpreted with respect to the category and the context of this data. So IE can kind of be seen as part of a greater puzzle, which deals with the problem of devising automatic methods for text management beyond just its transmission or storage and the way that it's displayed. So it can be used for the extraction of entities from the text, such as names of people, organization, location, the relationships between entities, attributes, events, and relationships. And the way to evaluate this can be the relevance of results, and this is called precision and recall. And so the discipline of information retrieval has developed several automatic methods, and this typically has some statistics involved in it. And another complementary approach is that of natural language processing. And this has actually helped to solve the problem of modeling human language processing with considerable success when taking into account the magnitude of the text. So in terms of both difficulty and emphasis, information extraction kind of deals with tasks in between both information retrieval and NLP. So that just helps to give you kind of a context as to how does information extraction kind of fit into the general context of things. Next, we have information retrieval. So this refers to finding and collecting relevant information from a variety of resources, usually documented in an unstructured format. So the complexity associated with natural language is especially key when retrieving textual information to satisfy the information needs of a particular user. And so this is why we arrive at textual information retrieval. And so a textual information retrieval system carries out a series of tasks in response to a specific query by the user. So we actually start out by indexing the collection of documents. So in this phase, NLP techniques are applied to sort of generate an index containing document descriptions. And normally each document is described through a set of terms that in theory best represents its content. Then the second step is when a user actually formulates their query, the system helps to analyze it, and if necessary, actually transforms it with the hope of representing the user's information needs in the same way as the document content is represented. In the third step, the system actually compares the description of each document with that of the query, and then presents the user with those documents whose descriptions are closest to the query description that was originally given by the user. And lastly, in the fourth step, the results are usually listed in this order of relevancy, that is by the level of similarity between the document and the descriptions of the query. So IR helps to extract relevant and associated patterns according to a given set of words or phrases. And so text classification, which is what we'll be focusing on, is this technique that involves designating pre-decided categories to free text documents that contain insights about the world. And the general purpose of text classification or categorization is to increase the detection of information that can lead to a better decision. For example, news stories are typically organized by subject categories or topics or geographical codes. And technical domains and subdomains often classify academic papers. But at the same time, patient reports in healthcare organizations are often indexed from multiple aspects, such as using taxonomies of disease categories, types of surgical procedures, insurance reimbursement codes, and so on. Another widespread application of text categorization is spam filtering. And this is where email messages are actually classified into the two categories of either spam or not spam. And this is something that we did as our data set from the first week, where we were discussing pre-processing in the first step of this NLP workflow. We actually had a spam or not spam data set, and that contained various SMS texts, but we can also use this in the email setting as well. We also have text clustering, and this technique is used to find groups of documents with similar content. And so it makes use of descriptors and descriptor extraction that are essentially sets of words that describe the contents within a particular cluster. So it is an unsupervised process that is responsible for classifying objects into groups called clusters, which consist of several documents. And dividing similar text into the same cluster kind of forms the basis of this entire method. And last, we move to text visualization. And in these methods, it can actually help to improve and simplify the discovery of relevant information. To represent individual documents or groups of documents, text flags are used to show the category of the document and to actually also show the density colors. And these are what are used to represent the category of the document. Visual text mining also puts large textual sources in a visual hierarchy. And in this way, the user can interact with the documents by zooming and scaling and viewing this overall hierarchy of all of the documents that we have as our textual source. And information visualization is very applicable to government to help identify terrorist networks or to find information about crimes. So it has several important applications in the real world. And these are some of these are some models that I have already mentioned, but just for you to see kind of how all of these very popular machine learning models and what exactly is their application. So just to name a few, we have naive Bayes, can be used for document classification. We have k-means that's used for clustering. For information extraction, we have conditional random fields and hidden Markov models. For document classification, we have actually quite a few. I already mentioned naive Bayes. We also have logistic regression, decision trees, neural networks, support vector machines, k-nearest neighbors. And then we also have a regression model as well. So that was a lot of information. I just want to give another breather to all of you guys before we move to the next section, where we're actually going to be talking about text classification. So text classification. So to start out with, so this week we're not going to get to the technical details of each algorithm, rather than focus on how to interpret and evaluate the result of each model for classification problems and how we can use this to draw the appropriate conclusion. So in the general model training approach, we gather the data, then we explore the data, then we prepare the data, and what we're going to be focusing on today is actually building, training, and evaluating the model. So the gather, explore, and prepare, we have kind of gone through this process already. And then after building, training, and evaluating the model, we can move further to tuning the hyperparameters and deploying the model. We won't be focusing on that today, but that's just some future steps that are typically done in this entire approach of training your own model. So to focus a bit more on building our model, so generally speaking, you can start building your model by splitting the data sets into test versus training sets. And depending on how much data you have, i.e. the number of observation or rows in your data that you have, you can split it by either 80-20, 30-70. So that means that 80% of your data is classified into the training set and 20% is classified into the test set, or the same for 70% training, 30% test. But general rule of thumb is either 80-20 or 70-30. And there's four main pieces of advice that's typically given for how to build a good machine learning model. So one is to keep it simple. So the first iteration of your model must be simple, and you want to make sure that you want to get the infrastructure right. And so the first model actually provides the biggest boost to whatever argument that you're making, and it doesn't need to be fancy or complex in any way. Some good questions to ask is, what is good and what is bad? What does that mean to your system? And how can you integrate your model into some larger application if you would like? Another thing is to choose simple features, and this will make it easier for you to ensure that the features actually reach your machine learning algorithm correctly. Also, you want to ensure that the features reach your model in any sort of server that you're deploying it into correctly. And also you want to make sure that if you're doing any sort of tuning of hyperparameters or learning weights, you also want to make sure that that learning process is happening accurately. Secondly, you want to detect any problems before you sort of increase the complexity of your models or exploit it in any way. Third, you want to design your metrics properly. So to start out with, you want to choose a very simple and attributable metric for your machine learning model. And so your machine learning objective should be something that is easy to measure. So you want to start by training on the simple machine learning objectives, and then consider having a layer on top of the first layer that will allow you to add additional logic. So next we'll actually be going into model evaluation. So model evaluation, in real life, the performance of a text classification model is very heavily dependent on the quality of your input data set and the type of training and test sets that you select. So it is very important to assure the quality of your labeled data is as accurate as possible. So model evaluation aims to estimate the generalization accuracy of your machine learning model on any future data. And when I mean future data, I mean any unseen or out of sample data. And model evaluation metrics are required to quantify the performance of your model. And this choice of which evaluation metric that you choose does depend on the given machine learning task, which can be classification, regression, ranking, clustering, etc. And so some metrics such as precision and recall are useful for multiple tasks. For supervised learning, such as classification and regression, you can have several applications, and you can use precision and recall, but perhaps even more advanced metrics. So the ones we'll be using that I'll discuss the theory side of it right now, and Jayeeta will actually be doing the implementation of these in the second half of today. So we're going to have the confusion matrix and the ROC and AOC curves. So the confusion matrix is the summary of your prediction results in any sort of classification problem. So the number of correct and incorrect predictions are summarized with these count values and then broken down by each class. And so this is the key to the confusion matrix. It helps to show the ways in which your classification model might be confused in making predictions. And it gives us insight not only to the errors being made by a classifier, but more importantly, the types of errors that are being made. So kind of a short explanation on how to interpret a confusion matrix. So the diagonal elements represent the number of points for which, so these diagonal elements here, help to represent the number of points for which the predicted label is equal to the true label, while anything off of the diagonal was mislabeled by the classifier. Therefore, the higher the diagonal values of the confusion matrix, the better, indicating many predictions were made correctly. And so to give you some definitions of all the terms that are used here. So P is positive, as in the observation was positive. For example, is an apple. And N is for negative, so observation is not positive, meaning is not an apple. Then we have true positive, and this is where the observation was positive and it was predicted to be positive. Then we have false negative, and this is where the observation was positive, but we actually predicted negative. Then we have false positive, or FP, and this is where the observation is negative, but it was predicted positive. And lastly, we have true negative, and this is where the observation is negative, and we do predict it to be negative. And then we also have precision, which is basically a calculation of the true positive divided by true positive and the false positive, so the sum of those. Then we have the negative predictive value, which is the true negative divided by the sum of true negative and false negative. Then we have sensitivity, which is true positive over the sum of true positive and false negative. Specificity is true negative over the sum of true negative and false positive. And lastly, we have accuracy, which is true positive and true negative divided by the sum of all four of these terms. So if we were to think generally, if we have very high recall and very low precision, this means that most of the positive examples are correctly recognized, or a low false negative, but there are also a lot of false positives. If we have a low recall and a high precision, this shows that we actually miss a lot of the positive examples, so we have a high false negative. But those that we do predict as positive are indeed positive. So therefore, we have a low false positive rate. And then here we have an F1 score. And so this is where we actually combine precision and recall, and we actually get this measurement that represents both of them. So we calculate this F1 score by taking the harmonic mean in place of the arithmetic mean. And so this F1 score will always be nearer to the smaller value of either the precision or the recall. I hope that helped to clear up kind of everything that's going on in this table. There's a lot going on here, but basically it just helps you to get a lot more insight into the classification task at hand, and helps you understand the types of errors that are being made. And lastly, we have ROC and AUC. So this AUC and ROC curve is a performance measurement for classification problems, and this can be done at various threshold settings. So ROC is a probability curve, and AUC actually helps to represent the degree or measure of separability. So it tells you how much the model is actually capable of distinguishing between classes, and the area under the ROC curve is a performance metric for measuring the ability of a binary classifier to discriminate between positive and negative classifiers, or classes, sorry. So the higher the AUC, the better the model is at predicting zeros as zeros and ones as ones. So for an analogy, the higher your AUC, the better the model is at distinguishing between patients that have a disease and patients that do not have that disease. The ROC is typically plotted with the TPR against the FPR, and this is where the TPR is on the y-axis and FPR is on the x-axis. And a very excellent model has an AOC near to the 1, which means it has a very high degree of separability. A very poor model is an AOC that's very close to 0, and this means it has the worst possible measure of separability between your two different classes. In fact, it means that it's actually reciprocating the result, and so it's predicting zeros as ones and ones as zeros. And then when you have an AUC of 0.5 or 50%, it means that the model has no class separation capacity whatsoever. So it's basically just guessing, your 50-50 probability. It's not really learning anything. Sensitivity and specificity also come into play here. And so they're actually inversely proportional to each other. So when we increase sensitivity, specificity actually decreases, and vice versa. We also have this threshold that is typically determined for your ROC curve. And when we decrease the threshold, we get more positive values. And so this then increases the sensitivity and decreases the specificity. Similarly, if you were to increase the threshold, we get the opposite result, where we get more negative results, we get more negative values. And so thus we get higher specificity, but we get lower sensitivity. And so as we know, FPR is 1 minus specificity. So when we actually increase the TPR, the FPR also increases and vice versa. So those are just some general things you can kind of understand about ROC and AUC, but they're very, very useful, very widely used in the real world when people are developing machine learning models. And we'll be using these as well in the second half of today's session when we'll be implementing in Google Colab. So just for some quick theory wrap up and then next steps, and then we'll be taking a 10-minute break, and then Jayeeta will jump in for the implementation. So today we went over the different types of machine learning. As I said, there's 4 main categories, but the ones we went over today were supervised, unsupervised, semi-supervised, and reinforcement learning. And today we'll be focusing on a supervised text classification task. And lastly, we also went a little bit deeper into supervised learning and what are all of its applications. And then we went into text mining and how it relates to text analysis and text analytics, and how important it is for several companies and organizations. And lastly, we went into text classification, the popular models that are used, and we also went into how to build a machine learning model and how we can evaluate this model. And the 2 metrics we went over are, or the 2 general evaluation methodologies we went over is the confusion matrix and the ROC and the AUC curve. So that was a lot of material. I hope everyone is hanging in there. Let's take a 10-minute break at this point. We're almost at the 1-hour mark. And when we come back, we will be jumping into the Google Colab project. The link to the notebook is right here, and it'll be shared in the chat as well. And I will be jumping off, and Jayeeta will be taking over for the second half. Thank you, everyone, for joining today. Just want to say thanks again. And let's take a 10-minute break. So it's on the 58 mark. So I guess for me, I'm in Pacific time. So it's 12:58. So at 1:08, we can resume with the implementation. Thanks, everyone.
Hi, everyone. So welcome back to the second half of the session. I guess we went over a lot of what's the meaning of machine learning and what are some of the applications. Rishika did a great job explaining some of the very useful use cases that we see right now, like including text classification, information retrieval. And for this session's hands-on Colab notebook, we're going to focus on one particular area, which is text classification using our dataset that we have downloaded from Kaggle. So before we jump into how we do that in Kaggle, let's just take a look on how you can access this dataset. I'm sure you must have received the link of the Colab notebook in the chat section. So when you go to the section, you click on this PYNB notebook file. So if you just go and quickly do Colab Google, it comes up like this. And you can just, if you click on it, copy the link from the link that you have received in the chat. Shimona must have shared it. And you can just paste the link here, press enter, and it'll just pop up. Okay, let's see. Okay, you have to go to the GitHub link. Sorry for that. You have to first go to the GitHub link. In all the examples that you have examples, recent, Google Drive, but we want to access the GitHub. So you go to the GitHub tab, press paste the link, and then if you search, it just pops open the notebook. that you see all of this here. So you would want to access this one, which is week 5 NLP supervised text classification. If you click on it, it just opens up here. Great. So I hope all of you have, you can access the the Colab notebook right now. If you cannot, let me know, and I can show you again how to do that. But let's go forward and start with this session. So here we are utilizing a data set from Kaggle, which is a fake news data set, to give you an idea about how it looks like. Here is the whole list, and you see that they have mentioned in the description that there is a train file and there is a test file. So we're going to be working with only these two files today. So the training file, if you roll down and click on the train section here, you see that it gives a gist of how the Excel or the CSV file that you download from here would look like. And here is like the column name. So there's a column called ID, which kind of like shows 0, 1, 2, 3, a numerical ID for all the text documents that they have. Then there is title, which like highlights the name of the news article's title. There is the author, who the author of the news article is, the full text or the full body. And then you see that there is another column called label. So you would see that this is a label termed as 0 and 1. So from here and from the clarifications that we got from the first half of the session, we know that this is a binary class problem because we have two classes, 0 and 1. And if you go up in the description section, you see here that the label means that if it's marked as 1, that means it's unreliable, that it's might be a fake news, and 0 means it's a reliable and coming from a a known source, and the news is correct. So the test file also has the same columns, but it do not have the final label column. So that's the idea, right? So we're going to be using the train set, utilize the tagged column list, and kind of predict the final label for the test CSV file. Great. So you can so if you see here, I kind of mentioned all the details here and how you can download the data. So you can download the train and test CV, and this is how you can, kind of connect and upload your data set into your Google Colab. So you can just upload from here, and you would see both the documents, train and test file uploaded there. Once you have that, what you can do is like quickly check which folder of the Google Notebook it's referring to. So this is how you can do it. These are some of these steps that we went through in some of the previous sessions as well, but just for the sake of continuity, we will follow through and see how we can go at it. So once you do PWD, you see that the /content is the folder which the Google Colab is kind of referencing to whenever you're trying to upload and access any data. When you do ls, which is like listing out what are the kind of files that's there inside the underscore content folder, you see that the test CSV and the train CSV exists here. Great. So we're going to do some preliminary loading of the data set, of course, and describe data set visualization of it like we did in the previous sections, just to kind of get a bigger understanding in doing the descriptive statistics for our data set. Let's see how we can do that. Okay, so these are some of the libraries that we'll be using, pandas and numpy being the bigger ones. We imported CSV, matplotlib, and seaborn for some of the visualizations that we would do. These are some of the common, I'm sure you're familiar with it by now, some of the libraries from NLTK, and that we are downloading the stop words and the tokenizations from. And here are, if you see at the end of, here are some of the libraries that we are accessing from sklearn, which includes all the models that we are going to try and build. So we would kind of focus on logistic regression today, but I included these models and showed you in one step on how you can call those models and how the accuracy scores would look for them, just for you to review and kind of like have a deeper look later when you have some more time and research on each of these algorithms separately. So let's start. So this is the train file that we are reading from the train.csv that we downloaded from the Kaggle website. Some of the similar data cleaning that we did here was just to, kind of strip if there are any leading or trailing spaces in the context or in the CSV file for each of those columns, because sometimes that kind of like hampers on how we are calling the data and throws unnecessary errors. So here we are printing out how many rows and columns. So we see that we have 20,800 rows and 5 columns in the training set. After that, what we did here was just, a precautionary step just to remove if there are any empty rows. We do not want the CSV to come across errors like sudden end. You will see that sometimes it comes up like that. So here what we are doing basically dropping any row that have like, axis 0 means that going row wise. If any of it has a null value, then it'll just kind of, drop it. But we see that they're all cool. There's no such empty rows that's available. So we have all the full data set that we have loaded in here. Similarly, we do it for the test set as well. We run the same steps and we see that the test CSV file has 5,200 rows and 4 columns like we discussed before, because you see that the one column that's missing here is the label column. So this is the test file, and we need to predict the label value for the text files here. Great. So you can just do, train.info and test.info to see what kind of column types, data types they are, what are the counts and number of values, non-null values that they have. So here we are, kind of trying to measure if there are any null values. So what you can do is that when you call dot is null and dot sum, it kinds of gives you the total summation of the null values that's available for each of those columns. Now, if you see, the title has 558, whereas the text has 39, like 39 rows that have null values. So since this is a text classification problem, we would want to have as much clean data with us as possible. And our major focus of understanding if a news is fake or not would come from the text column, since it has the most number of words. And usually in any machine learning or classification problem, the bigger and the cleaner the data set that you have, it kind of like enhances the results that you get and kind of makes the whole process more smoother and easier to, make sure that if it's predicting it correctly or not. So since we are focusing on the text column here, what I did here is that kind of picked only those columns in the text, only those rows from the text columns that is not NA. So what this whole function kind of does is kind of takes out all the columns, all the rows basically that have where the column text value has NA. And if you see, when I print it out now, what's the train shape, it kind of gives you 20761, which is slightly less than what we had here, which is 20800. So there were those number of rows that kind of we dropped because the text values were empty. Now when we check it again, and we did the similar thing with text, and we saw that there was, I think we can see how many here. See, there were 7 rows that were that had the value null for the text column in the test dataset. And then when we and in this step, when we remove them, now we have the total number of final rows. Now I am checking it again, once again, just to show you what we would do in the next step so that the clarity remains on why we are doing it again. So this step is null.sum in train shows that we still have title and author as null values, right? So our idea is to kind of aggregate as much text from the whole row and include not only the text, but also the title and the author. So if we drop all the title and the author, we will have like, losing a big chunk of our data set, which we do not want to do. That's why sometimes based on your use cases and applications, we need to decide if we want to drop our rows, or we want to maybe, if it's not a text data, if we want to do a regression or maybe a mean and kind of predict the values for the rows that have null values. But in this case, since it's a text file or text data, what we kind of did is replace the null values with a blank space, so that when we are trying to vectorize it, the vectorizer, TF-IDF vectorizer, the count vectorizer, all the methods that we discussed in previous sessions cannot handle null values. So if you pass in the training set null values, it'll throw you a big error. And to avoid that, so that's why I mentioned here, it's not crucial, but we want to keep the data for the title and the author as well, to include, for at least those one that has the data of the full and not drop them. So we kind of fill NA is the method that you can call, and then with a within bracket space bar, so that it kind of fills all the values like that. So now when you call train.isSum and num, you would see that there is 0 because it doesn't find null values anywhere, because it has kind of replaced null values with spaces. Then we go ahead with the pre-processing steps. These are some of the similar steps that we did in previous weeks, but just to, kind of go through the whole process of data cleaning and preparing the data for, to be pushed into the model and going forward with it. So the first step is contraction mapping. Now we are using this library. You can install it with pip install contractions, but I would like to highlight one quick thing here. When we were kind of working through the whole process, we found that there were some peculiar words that was kind of failing when it goes into the contraction mapping library. The team found that we had like an edge case in this example as this word. You can see that there are some special characters in this word that the contraction mapping library was not able to handle and was throwing out some errors. You can, kind of run and print out all the words that goes through and kind of highlight and see which words they're getting stuck to. So that's why data cleaning and, pre-processing the data and kind of knowing your data helps a lot in terms of like identifying these kinds of edge cases, because like in real life also, when you work with a lot of data, you will not get data which is like very clean and prim and proper, but you need to kind of like clean it up, review it, and see where you can map it back to a good value where it is edge case. So in this case, what we're doing is we're kind of like deleting all the rows. Like that's it says that not select rows that contains the string, this string, I don't even know how to pronounce it, some weird character within the train text column. So now what this train value would have is it'll have only those columns and all the columns and only those rows that do not contain this word that you see here. Great. So now that I just again, kind of printed the shape of it, you see that maybe 7 or 8 rows must have dropped because of removal of this word, but that's fine. If it's, if it's a business case sensitive use case, what you're dealing with in the real life, what you can do it is like kind of maybe use a translation methodology to kind of translate that word, or create like a mapping with it in an English word, so that you can like the contraction mapping process can work on that step as well. So when we kind of evaluated, we found that this word exists in both the test and the train file. So we kind of did the same procedure here again in the test set as well. And then you see how the test set looks like right now. Now, yeah, so as I was in the next step, what I mentioned before is like we would want to keep the maximum amount of text that we have at our hand for the training section, right? So for the train, what we are doing is we are kind of creating a new column called total, and concatenating all the text that we have within title, author, and text. If you see here, like you see the author here shows empty and it doesn't show null or NaN. That's because we kind of, cleaned it up and replaced all the null values as spaces. Great. So I just printed it out, and said, okay, it's done. We combined the column title, author, and text in one column for training data to have more content. So so now that we have, the train total as our final column that have all the text, we are applying the contraction like we did in the previous sessions, and we also did it for the text section as well. if you see the head here, this is how it looks. It's like in a list format, and because it broke it down, split it by spaces, and then applied the contraction to kind of map it out into to full words for all the words that was in a constructed manner, like doesn't and wouldn't and etc. So here, because we want now, now that it's clean and all the contractions are mapped, so we would want to have like proper string format. So we're kind of mapping it here. The function is basically calling and saying that okay, map the str and for each of the train total, and we are also applying the same in the test and test total section. And now when I print it out, you see that we have id, label, and total. So a quick thing that I guess that'll come later. We'll discuss about it on why we did that. So let's move ahead, and we did the same for the test column as well. Now the noise cleaning is something that we discussed that we can do using regex or regex, however you want to mention. So you kind of utilize it with .str.lower, and then you apply this regex that kind of cleans it from the section. And what this means is, here is the quick explanation of it. It kind of finds what are the white spaces, the digits, and if it finds any match characters, that's literal characters, and also how many times it has matched, it will kind of remove it from the whole data set. So now we have like a lowercase data, and much cleaner without any special characters, cleaned by the regex method. And we applied this for both training and the test set. So for the tokenization, we apply the NLTK tokenization. So for this methodology, or the answer that we're trying to solve in this use case, we do not actually kind of need to like showcase the total tokenization or the tokenization method. But why we are doing it is to to ensure that we are doing the required steps of data cleaning, data pre-processing, and visualizing to kind of get the descriptive statistics of the data, so that we know it more in details, and kind of find insights from it without like before jumping into the machine learning side of it at once. So here is something we did in the last section as well. So we apply word tokenization method, and you have we created another a column called total tokenized that have like the list of all the strings. Now we applied that for both train and test. And again, like we discussed before, these are the stop words model that you can download from NLTK. And before moving the stop words, is kind of always crucial. For each business case, data is different. So before removing any of the stop words, you would want to know that what those stop words are. For our case, we would see that it's very much similar to what we discussed last week. The, to, of, and these are some of the very common that comes up in all news articles, and it's kind of the same for both our training and the test data set. So you can just plot it here and visualize, and for some of the cases, some words may come up that would like kind of give you more perspective for your use cases, and say that okay, hey, I don't want to delete this word, and maybe I'll exclude this word from the from our stop words list, and or maybe add more, like we did last week, where we added words like New York and words like Brightbird, because they were like very heavily used words in all the article titles, and that was kind of like skewing our similarity scoring methodologies. You can go and refer to the code, and you will see that how we did that. Great. So we also did a quick chart out of the non-stop words of how it looks and what are the top ones. You see that there are said and Mr. and would. So these are some of the context words that needs to be remained, and it's not something like New York Post or name of any particular organization that's publishing the news article. So we would not be kind of removing any of these words from the our corpus, and we would leave it as it is. This is just kind of give you a way of how you can visualize and kind of find insights from it. So here in the next steps, we are removing the stop words. We're kind of applying in the same way, calling a lambda function, calling each word for the particular x. X here is the, the the total tokenized map, and then we are excluding if it exists in stop words list, then we exclude it, otherwise we keep it as is. So here we have and then in the next step we are kind of joining and creating a big sentence out of it, like we did for the previous section. And now our this has like all the removed stop words and removed special characters, and it's good to go now. And we did the same for test file as well, simultaneously, and you print out test and you see you have like uh, similar columns here. Now, before I go into the next step, I would want to highlight one more thing. Sometimes it happens, and it definitely depends on case to case basis, that you test without removing the stop words, and you also test without with removing the stop words. So some of my experience have shown that in some of niche character based files, removing the stop words can kind of sometimes take away the meaning of the sentence if it's like not let's say general English, or not general news article, and maybe a business document or maybe a legal document. So you have to be very careful and like kind of measure and see what are the kinds of vectors that's coming out from utilizing the stop words or without utilizing the removing the stop words. So in this case, that's why I kept both the column total as well as total tokenized join, which is like this total have all the cleaned up rows, but just that it has the stop words with them, and this one do not have. Great. So again, for this step, for kind of finding out the tags or the POS tags that we discussed in week 2 and week 3, to see how it affects and how our the whole document set has distribution for each of these POS tags. It's not something that you have to do, but it's highly recommended that you do all these pre-steps so that you are very much aware of your whole data set and know exactly what to do where. So here basically we are calling each from both the train and the test file, from the column total tokenize, and kind of doing the position the POS tags here. What we do here, as we discussed in week 2 and 3, is that call the yellow brick, which is like a great library to kind of visualize your POS tag visualizations. It just gives you a count for all your test sets. So this is for the training set, and it says that in the x-axis it's the pen, tree, bank, part of speech tags, and in the y-axis is the count for each of these POS tags. And you see that, as we know in a news article, nouns, verbs, adjectives, these are kind of very dominant POS tags that should be there, because we are always talking about a people, name of a person, etc. We also did the similar for test, and we see that the distribution kind of remains the same. Noun, verb, and adjectives kind of dominates, and we also have some kinds of prepositions and digits along with that. Great. And here is like, a reference to the book that you can, always go back and read about POS tags and universal tagger. Now we move into the text classification methodology and how we go about it. Say we have this train label, which is the label column that we had in the training data set, and we are kind of like want to understand what's the distribution between rows that have been tagged as 0 and 1, which is like fake or not fake. So when we do the value counts here, we see that 0, which is like reliable, I think, and 1 is non-reliable. So 0 is like a true news and 1 is like a fake news. We see that the distribution is pretty good and there is not too much skewness. So the skewness of the data can happen for a lot of data sets, like consider a medical data set where you're kind of predicting if a person has cancer or not. So in those kinds of training models, the data sets sometimes tend to have a pure representation of people with not cancer versus having cancer. So there are multiple ways on how you can handle those kinds of data sets. You can research more about that, but this is just to highlight that for the data set that we are working currently with, the distribution is pretty good and pretty almost equitable. So here we're just printing it out how it looks, and we see that yeah, both our labels have very good counts and equilibrium counts of documents that we need to train it on. So here we are doing another thing. What we are doing here is, kind of creating a separate column, which is called the targets. This is creating a series or a NumPy series called targets. What we are calling that from is the label column from the training data chart that we had, and calling all the values from that. So basically what we are doing here is saying that we are, breaking up our training set into all the other columns versus another target column that we want to predict our model with. And once we do that, we're kind of, dropping the label with axis one. Axis one, the operation happens column wise, and in place true, that means the train head will now have, ID, the total, the total, the total tokenized and the total tokenized join columns. And you see that the label column here has vanished because now it has come into the target and we have dropped it from our training section. Now, remember we went through a lot of theory about TF-IDF and how we did n-grams and how we did count vectorization using bag-of-word model and similar in week 2 and week 3, but I just wanted to give you a highlight here so that it kind of refreshes your memory. You can also access this use case documentation by sklearn, where they talk fully about what TF-IDF transformer is doing, what are the kinds of parameters you can pass through it, and what are the kinds of applications that there are some use cases that if you want to go step by step and maybe apply it in smaller chunks of code, you can work through this and then come back to the notebook here to see that how we are kind of utilizing those features. So the overall idea, what we are trying to achieve here is we are calling or creating a variable called transformer and calling the TF-IDF transformer library from sklearn. This is the whole section here. What it does is it's basically transforms the count metrics that we did into a TF-IDF representation. So if you remember, we discussed in TF-IDF if a frequency of word depends, kind of infers what is the kind of importance it has in the document, and the rarer the word, the focus would be that that's kind of precious word and kind of explains key terminologies that come up, and words like would, should, and I went there, similar terms would be given lower values of importance based on the higher number of occurrences that it have been found in the whole documentation. And here then what I'm doing is calling a count vectorizer another variable where I'm kind of doing a count vectorization based on n-gram range. So if you all remember, we discussed n-grams can be, unigram, bigram, or trigram, depending on the values that you are passing. And why we want to do it is kind of limiting our whole corpus, because if you only do count based on, only particular singular tokens, you'll have a huge corpus, and sometimes it doesn't help in understanding how important a word is. But sometimes when you do say n-grams, if two words, like if you're doing a bigram, say in this example, if you're doing a bigram and two words continuously come up a lot of times, then that would be given more preference, keeping your corpus length to a good amount of and not exaggerating it to everything that you have. So it kind of brings it down to a very consumable format, and also gives you higher amount of insight to what that those two words might mean. So I kind of used it in a different format here, like 1,2, and just to give you an example of what that means, since it's not directly a unigram or a bigram, but it's like a combination of both. So here's a quick example. Say if you have a sentence that an apple a day keeps the doctor away, when you call n-gram 1, 2 and you fit it to the discount vectorization, if you print out the vocabulary, what you would get is, look at this, you would get an as 0 because it's kind of doing it first as in unigram format. So you have all the individual tokens, and apple, day, keeps, etc. And then you would see that it has again a separate set of combination with bigrams. So it's basically doing both. So you can also have instead of 1 as 3 if that maps to your data more accurately, because sometimes you have sometimes some data structures have like bigger words that explains it properly. Like if you have all say country name or maybe city names, and if it's like New York City, or you have similar kind of data, it might sometimes help by doing it in a 1 comma trigram way, so that, or by 2 comma 3 way, so that it kind of captures all the context in a good format in that way. So yeah, it's like a combination of unigram as well as bigram, and kind of gives you that whole list of vocabulary in the similar way. So in our case, what we are doing is, the count vectorizer that we created using the ngram range 1 comma 2, we are fitting it to our train.total column. We're calling all the values from this column, and we're using the fit.transform method. So what it does is that it passes this the idea that you have to break down your whole column into this way, and fits it into that. So basically now it's transformed into a vocabulary that looks something similar to this. Okay, now once we have this, now we apply our TF-IDF on top of that. So we are creating then the train TF-IDF function, and we're the fit dot function, which is the transformer. Here the transformer you see is the TF-IDF transformer that we called from sklearn, and we are fitting that into our train counts, which is the count vectorized format. Great, so now the idea is we have transformed all our text data into a vectorized methodology and a numerical format that the machine learning algorithm can consume very easily. So what are the next steps? We need to go forward and then create a train test split. So Rishika mentioned that there are multiple ways. You can do 80-20, you can do 70-30, depending on some of the use cases that you have at hand. And here, this is how you can do it. So sklearn, under model selection, they have this method called train test split. So if you open this up, you would see that they have given good examples of what are some of the parameters, what is the test size, train size, etc. So you kind of can control how big the training set and the test set should be. If you don't want to mention anything, then it just kinds of puts the test set as 0.25 and the rest as, so train size would be then 1 minus 0.25. And that's what we kind of did in our section as well here. We didn't mention any train test size, and we just mentioned the random state 0, so that it has like, one particular seed that it would refer to every time that it runs the model, so that we have a fixed number of ways to look at it. So here we're creating, the output of this whole, the output of this whole function would give you 4 variables. The first is the X train variable, the X test variable. These are all coming from the train.csv file that you have. And then this is the Y train, which is the label for the training set. And this is the Y test, against which we are going to be predicting and checking how much of the prediction has come true, and create all our confusion metrics and accuracy metrics, etc. So here, if you see that I've highlighted some of the models that you can utilize. Extra trees classifier, is kind of an estimator how many trees it will have, and jobs would be how many runs of it will do to kind of fit the data. And all these models are inbuilt within scikit-learn. You can call these models and dot fit to your X train and Y train. This is an important concept, that you are only passing the train values and kind of creating that whole matrix that would kind of help you to predict the labels for the test set of the data. So if you kind of print out, we did it for all the models, you print out the accuracy of this classifier on train set. Is like, how do you do that? You kind of call it dot score. Dot score is the method that when you call for X train and Y train, it'll show you how much percentage was, or what's the score value that all the methods that you kind of trained, and how much accuracy did it had, and did it tag it correctly, did it tag it falsely. Now in some of the situations, I would like to highlight that maybe looking at it, it looks at, wow, it's like total 1. That means our model is amazing, our model is doing great, all the the predictions from our training data is coming true. But a very key concept to remember here is called overfitting. Sometimes when we have not too much data, we kind of and we imply or apply a lot of big trees or decision trees or maybe random forests. Sometimes it happens that, like we said, that how does the machine learning understand? It kind of sees the data every time and kind of predicts from there. So by constantly repeating and looking at the same data again and again, it kinds of memorizes it too well and saying that, okay, if you show me this data, then I'm going to be like predicting it with 100% accuracy. But that's not the point of our training. The methodology, the training methodology should be that given a set of training data, you have to be able to predict the test data to a higher level of accuracy, which you have not seen in your documentation at all before. So it's a very new data set, and there are no, maybe some cases can happen that there are no intersection of data content, or maybe all the vectors or all the tokens that we utilized are like completely different. So how do you do that? So to keep that in mind, we applied like maybe an error boost. We also tried out random forest. These are all different versions of machine learning and supervised learning algorithms. You would find like great documentation in scikit-learn's documentation here. You can go through each of it and then see that if you have any difficulty understanding some of the algorithms, you can come back and ask us. But we won't go too deep here. What we will do here is kind of jump to logistic regression, because logistic regression is something that comes to mind first when you have a binary data set. And this is the first, I would say, the simple baseline model that you should always try to perfect before you kind of jump into any other complicated methodology like say random forest or decision trees, which has multiple layers of hidden inferences that needs to be done properly. But having a baseline model always helps to kind of see how your model predictions are growing over simple to complicated models, and how or what else fine tuning you can do at the later part of the model to make that work much better. So this is also a very simple implementation. You should just call from the sklearn linear model, because regression is a linear model. It's a binary classifier, and you kind of fit here as X train and Y train. And we print out, we see that we do have a training set recall, like a precision of 1, but for a test set, we have 0.98, which feels a little better if you go and see what we had for the first ones, which we discussed. Like it had 8.84, 0.96, 0.81, 0.75, and 0.98. So this does not necessarily mean that at all circumstances, or if you have like more data sets or more data rows, if you add on to the test, it'll have the same number of accuracy here. But it's kind of giving us an overview of idea that now that we have trained the data, fit the data into our training, and kind of trying to predict the labels from our test part of the data, and see that how much of it was like correctly labeled or correctly tagged back to. So for the next step, there were some of the ways that you can measure the model performance. Rishika went about it and described a little bit of like what true positive and false positives mean, what are the precision, recall, and F1 scores. So for this one, what we are looking here, if you see I printed out here, is like the accuracy. So accuracy is basically the the fraction of correct predictions. So that would give you the correct predictions divided by like the total number of data points that you had passed on for the model to predict for. So here is the way that you can kind of get the score of the model. So here is the logreg model that we created. Here the logreg is the value that's fit to the logistic regression model with our training data set. And when you pass the X test and Y test, X test is like the ones that they didn't see the values or didn't have the labels, and kind of predicted the labels, and we verified it with what the values existed in Y test, which were the given values, or in other words, it's called the ground truth. So you're kind of comparing what the model predicted and comparing it with the ground truth that you already have in your trained data set. Sometimes creating this ground truth data is expensive. Like we discussed in the first half as well, that sometimes you need, domain subject matter experts, the resources, the time, uh, proper cleaning and tagging takes a lot of use cases, and the big chunk of the time to kind of create a good model. So yeah, so we need to be aware of all these scenarios that goes on while trying and building a machine learning problem for a real life use case. But for this case, yeah, you just print the score and you see that okay, 97 and percentage is like correct. So from here, accuracy score is basically another version of calling of how you're creating the logistic score. Here is just the percentage sign, and I just wanted to show it here because this is how you can also call under sklearn has a great metrics subdomains where you can call accuracy functions, and you kind of predict the x tests, and then you pass it with the predictions, and you kind of find the accuracy values from there. These are some of the two ways that you can find out the accuracy scores. For the confusion metrics, this is like, a table that's often used to describe the performance of, to basically visualize and show you that what's the, difference between how many false positive and false negatives we had, how many true labels were detected, and how many false labels were detected. So you can very easily call it from the metric section, and you call it as dot confusion matrix. You pass your y-test and the predictions that you had, and then you see it in a an array format, but it's kind of not visually appealing. So what you can do in utilizing this matrix that you created, you kind of plot it using Seaborn. You can also do it or also plot it using matplotlib, but here in Seaborn you can very easily do it by this is just to put the fig size as 9 to 9 so that it's big and good for us. It's clean diagram for us to review. And this 1 second. Okay, so here what you're doing basically, so you're calling a heat map. You're calling this CM, which is the matrix that you created here in the confusion matrix section. And what you're doing here is like putting the Y label, which is the actual label, and the X label, which is the predicted label. And then you're kind of calculating the accuracy score for each. Now, if you look at this chart, like Rishika also mentioned, and she went through some of what each of these slabs mean. But if you look, this is how we can kind of interpret it from this chart. So here you see the predicted label was 0 and the actual label was also 0. That means both the news was not fake, it was a believable news, and the model predicted that it was a correct news. So that's why it falls under this first quadrant of this chart. And that's why it says you can successfully predicted 2530 positives. So this would be like all the positive outcomes. The second one would be 2537. So here you see the predicted label was 1, that this is a fake news, and we don't know if it's true. Like we don't know, like when we pass it to the model actually predicted that it is also 1. So 1 and 1 gives you this quadrant of the chart, and then it gives you the total predicted 2527 negatives. Now the idea comes with these two quadrants that's left. The first is, say the news was 0, that it's a reliable news, but the model predicted that it was a false news. So it turned a true news into a fake news, which is 77. And here the news was 0, which means that it was reliable news. The prediction was that it was a reliable news, but actually it was a fake news, which was 45. So if you look at it from this context, it might feel that, oh, so what would happen if I, kind of like predict a news as a fake, or a fake news as a true news? Sometimes in applications like mostly, like say disease understanding or classification, if a person has some kind of disease or not, these scores matter a lot. So sometimes the accuracy scores are not enough. So that's when you kind of go and kind of apply precision recall and then F1 scores to kind of evaluate how well the model is handling and how many number of true false negatives and false positives are available. So in this case, maybe for us, it's not, a life-threatening situation that we need to, be scared about it too much, because sometimes it can get misaligned based on looking at similar contextual data. So the next step then, after we have built the baseline model, then comes some other like word2vec. You can utilize doc2vec for creating more closer vector spaces of similarity, and maybe utilizing that as the next step of creating the classification model. But for the baseline, it works pretty decent for the use case that we have now. But for other use cases, like I mentioned before, it might be too risky, and we need to focus on that as well. And at the last stage, I just kind of like created a data frame called prediction, and put that how many counts of IDs were tested as tagged as 0 versus 1, and we see the numbers here. So if you take out the count values from here, you will see all the list of IDs with all the respective list of test labels, which are 0 versus 1. Yeah, so this was like an overview of the how you can take a very clean data set, like moderately clean, that we had from the Kaggle data set, and kind of implement a very high level or a baseline logistic regression model. You can utilize, or maybe like take a deeper look at some of these other methodologies that we mentioned here. Sorry, I'm just going up and down. Yeah, like multinomial naive Bayesian. You can also look at random forest classification and how it differs from logistic regression, but it entirely depends on your data set. That's why we say that once you start working with multiple data sets, you would know that which model fits which data the most. And that's how you choose your data, and maybe run it with multiple data and see that which gives you the best model, the best output, and by creating all these metric scores like we discussed here at the end. Yeah, so I would recommend you guys like take a look at the resources. They have like some of very good implementation. This project has like kind of full pipeline of how you can scrape if you want to scrape your own news data, and kind of build it from top-down approach. There's a lot of documentation about how you can do that, and you can review them and get back to us if you have any more questions. Great, so I guess that was all from my side, and I'm going to stop sharing my screen and see if there's any questions you have, or any questions that I can answer. I'm just opening up my Q&A. Yeah. Oh, I see that Rishika did a great job and she answered almost all your questions. So great. Okay, I guess we went through a lot of concepts here and a lot of ideas and algorithms, but at the end of the day, it all depends on what kind of data you have and what kind of analysis you want to do. But we would really encourage that always do it step by step. Make sure that you are kind of doing it, cleaning the data, ensuring that you visualize it correctly so that you understand the data in a good way. And that's like the most important part for making sure that you have the whole process under control, and only then you can like choose the best model that works for your use case. Great, so do refer to all the documentations that we shared, and read up on all the algorithms, and if you have any question, then we are there to help, and we'll try and help as much as possible. Great, so I guess that's me from my side. If okay, I see that there one question came up in the open section. Try and answer. So it says that as a way of going around, does it make sense to combine title and text columns as a way of going around big number of nulls? Yeah, so that's what actually we tried to do, and why we removed the null values where the text column was null, because say the text column is null, but you still have the title and the author. So that content wouldn't be too much, right? It will be only one single sentence and maybe the name of the author, but we don't have any other contextual information that the training model would benefit from. So that's why we kind of dropped all the columns that the text was for null, and kind of replaced for the rest of the columns like title and author, even if they are null, without removing them, just replacing them with a space character or any other character, so that we can at least utilize that instead of kind of dropping them. Yeah, but it entirely depends on your case-to-case basis. And like I mentioned before, sometimes you may not like drop any of it. You maybe have to kind of predict and apply another regression kind of model to kind of predict that what value fits for that particular column based on some of the other observations that have been seen in other rows with similar category functions. Great. Okay. Great. So thank you so much, everyone. Thank you for joining I guess, sorry, our next session is next Saturday, which is our last Saturday. We'll have a subject matter expert. She is marketing analytics manager in Facebook, and she's going to be talking about some of the applications of NLP that she has seen in her work, and walk us through what kinds of exciting challenges we can expect once we start working on multiple use cases. So great. Hope to see you all there. And appreciate you all spending your Saturday evening, night, morning with us from different time zones. And we'll see you next week. Thank you so much.